Just going to dive right in. So just going to go over kind of why might someone want to go storage, talk in details about kind of how to determine what is a load and what are the different characteristics of various loads, and then determine which ones we should pick. Because often when we're adding batteries for a home, you're not necessarily going to be backing up the whole house. You're going to be backing up a selection of loads from the house. So we'll talk about how you might go about doing that. So my name's Madeline. I am the energy storage manager for Soligent. I've been with Soligent since November, and I've been involved in solar plus storage since 2016. And my goal at Soligent is to really educate installers and homeowners to understand kind of what it means to add batteries to your solar system, or what it means to go straight out of the gate with solar and storage from the beginning of your installation, because there is a little bit more nuance to the discussion of batteries than there is just to having solar PV alone. And I want to help doing this by talking to customers, whether that be an installer or a homeowner, and connecting them with our various vendor partners, because we do have a pretty broad selection of products, and many different products can be used for a variety of use cases, but I want to make sure that the right product is being used for a given scenario. So that's just a little bit about me. So when we think about storage, why might someone want to either add a battery to their existing solar system or think about batteries right away? And there are typically a couple different categories you can consider. And I think the first one we want to look at is safety, and then we can also look at savings. So when we think about safety, how does storage enhance the safety of your system? Well, if we look at what's going on right now with the power safety shutoffs, the fact that it's storm season right now, we want to ensure that our house is going to be getting power during these outages. And adding batteries enables our system to isolate itself from the grid when the grid goes down, and be able to support itself through a battery or through a battery and a generator. And I do want to mention that Chris Kennedy of LoanPal hosted a webinar last week that really had to do about kind of understanding the emotions surrounding energy, and why energy stability and peace of mind are really kind of important factors to think about, particularly during these times of the pandemic. So I encourage anyone to check out that webinar that Chris had done with us last week. But just to dive a little bit more into the safety element. So resiliency. Resiliency is just a way of being kind of self-reliant and able to support yourself when the grid goes down. And we want a level of redundancy, if you will, to saying, okay, when the sun is up, when the grid is up, I have power from both my PV and from the grid. But then in the instance that the grid goes down and the sun is still up, I'm able to keep my PV running, and then when nighttime occurs, I can run off the batteries that have been storing my energy. Security and protection and peace of mind along those same lines of knowing that I'm going to have power no matter what happens, at least for some amount of time. Then regarding savings, there's the kind of feel-good element. By defecting from the grid, you're not using that grid power, and the grid power could be coming from many different sources. The grid power could be coming from wind, could be coming from solar. It also could be coming from fossil fuel generating sources. So by supporting yourself with your own power, you're really able to kind of close the loop on your energy needs by generating that with the PV on your rooftop and then storing it for times when you may be needing more power than when the sun is just up. So you can certainly lower costs if your electricity bill is high. That's an automatic booster. And then self-consumption, particularly if net metering is not available in your area. So let's talk about loads. We're going to just dive right in. So I really like these graphics because it uses a little bit of a metaphor on understanding what is voltage and what is current. So V equals IR may be a familiar equation to you. If not, we're learning something new today. So voltage is current times resistance. And I like using water as an analogy because you can think of flow and pressure as different ways. It's kind of tangible. It's a way that you can feel and understand what that means. So if we think about the pump and the pressure, that's our battery source. So this is going to be pumping out water, and this water is going to be flowing at a current level. So there's going to be an amps associated with this pressure. Then as we get narrower, the resistance or the load, what's taking up that power or that current is going to be kind of determined in this case by the sand or the narrowing of the diameter. So when we think about that in terms of electricity, we have our battery source, which is providing the volts. You know, if you think about even just like an alkaline battery, a little Duracell, or an Energizer battery, that AA, AAA, a 6-volt battery, a 9-volt battery, you know, we're thinking about that battery source in terms of volts. And that's going to be providing, and that's going to be coming from a current passing through some sort of resistance. And in our case, that's going to be the light bulb. Again, from a circuit perspective, V is just I times R. So when we're thinking about volts, particularly for AC volts, alternating current volts, 120 volts is a single phase value. And what does that mean? So a single phase power system is defined by having a single AC source with one voltage waveform. So that's why we refer to this as single phase, 120 single phase, because it's a single waveform. So then when 240 comes up, what does that mean? Why is that double? So split phase power systems is when you have multiple in-phase AC voltage sources connected in series, which delivers power to loads at more than one voltage. So in our case, it's split phase. It's multiple voltages with more than 2 wires. So often, if you are increasing your voltage, that may result in your amperage going down. And we'll talk about what amps means in a minute. So we have our 120 single phase, single waveform, and then we have our 240 split or multiple in-phase AC voltage sources. So we're really just thinking about a single or a double. So then where does the amps come in? Because then our next kind of equation that we want to think about in solar is volts times amps equals watts. So if we've understood that we have this AC waveform that's creating voltage, then our amp is coming with the current. And the amp is the rate of flow that this power is coming. So we have our volts times amps, and that's going to give us our power. But right now, we're talking about 120 or 240, and those voltage values are considered alternating current values. And the reason that we know this is if we look at an AC, this is just like let's just call this tube or a wire, if you will. We have this waveform, this sinusoidal wave, and it goes back and forth. And it goes back and forth at a very quick rate. So the hertz is the frequency of this alternating current. So it's the number of cycles over time. So let's use 60 hertz as an example, because most of our AC loads are running at a frequency of 60 hertz in the United States. So 60 hertz means that this electron is going back and forth along its wire 60 times in a second. So when you turn a light bulb on, you can't see it flickering 60 times in 1 second because the naked eye can't perceive that. But if you had, let's just say, a little circuit and you were able to tamp down the hertz to a single hertz, 1 hertz, you would see a light bulb flicker on, flicker off, 1 time per second, because 1 hertz would mean 1 cycle over a second. So the frequency at which alternating runs is just a hertz. It doesn't really mean anything. So I know in other countries, 50 hertz is the standard there. So again, 50, you still can't see 50 cycles in a single second. So it feels continuous, but it's really moving at a cycle. So in our case, if we look at this diagram, the grid is an alternating current source and our typical wall outlet. So anytime you're plugging something into your house, that's going to be an AC load. If we think about direct current, it's just a single source of power. So if we think about this diagram with the battery and the light bulb is representing a direct current diagram. So this would be a DC style light bulb. So you can get light bulbs that are either running off of alternating current or running off of direct current. So in this diagram, this battery, let's say it's a 6-volt battery, is providing 6 volts all the time. So we have our 6 volts coming into this light. So this current is nonstop in our case. It's a direct current going in one direction, and it's providing 6 volts all the time, and the light bulb is illuminating. So that's why over time we're not fluctuating. We're not going up and back. It's the same level. So things that use DC, I mean, these would be charged if we're thinking about a portable device. So a cell phone with a cell phone charger, anything that's being charged by a battery pack, the battery is going to be a DC source. So charging things with batteries, charging your laptop battery is a DC battery. Your cell phone has a DC battery. So you're going to have some sort of very small inverter to take the alternating current coming from your house to charge your cell phone, because your cell phone, the battery is a DC source. So again, hertz is related to alternating current and its unit of cycles over time. So when we think about these loads, they often have overcurrent protection, and these are 2 images of a breaker. Typical overcurrent protection is either a breaker or a fuse. And a fuse is similar to this, but you would have the fuse in a fuse holder. And so the fuse holder would look sort of like this, and you would insert the fuse into the fuse holder. So why might we use a single pole breaker? And if we think back to the previous slide, when you have 120 volts, we have a single AC source, a single voltage waveform. So we only need 1 pole for our breaker. So for this example, this is a square D 20 amp breaker. Typically these breakers, a single pole breaker would be between 15 and 20 amps if it's a 120 volt item, and it would have 1 hot wire and 1 neutral wire because it's got the single waveform. So then when we have larger loads, the loads that are representing 240 volts, those would be on a dual pole breaker because we need 2 breakers to be receiving the 2 hot wires that share the neutral. So we have 2 waveforms going on a single neutral. And for these breakers, the 240 volt dual pole breakers, these are typically, you'll get a between 20 and 60 amp for your dual pole breaker. So this is an example of a 40 amp dual pole breaker. And when do you use a dual pole breaker? Typically it's for larger appliances, and those include larger HVAC, electric dryers, electric ranges, typically, like a rule of thumb I like to use other than large HVAC, and often pumps. So large HVAC and pumps often are 240 volt loads. And then anything with a heating appliance. So a large appliance that has a heating apparatus. So again, if we look at the dryer, an electric dryer is heating that up to dry your clothes. An electric range, so that would be an oven or a stove top, that definitely is using a lot of power to create heat. And then a water heater is using electricity to heat up your water. So again, heating applications in a large scale are often 240 volts, and those would require a dual pole breaker in your service panel. So let's talk about different loads. I want to just look at a bunch. So in this case, if we're thinking about an emergency, and what do I really want to consider? What do I want to work? I want to be able to turn a light switch on. Maybe it's a single light in my whole house, but I really want some illumination when the grid goes down, when an emergency strikes. If you absolutely need your television, that may be something you're including on your critical loads. And then I'm going to add a garage door opener as well. So let's talk about different, what are the wattages, what are the power needs of these different loads? So if we look at lighting, this kind of pendant light I found is an LED. So light emitting diodes are the most efficient form of lighting right now that's commercially available. And this particular lighting appliance was listed at 43 watts, and that's going to be a single phase volt. 43 watts for a single light, and this one in particular was rated to 700, I want to say 750 lumens. So a decent level of brightness, and only 43 watts. So it's very modest. When we look at this, I think this is a compact fluorescent or an incandescent, like an incandescent or a halogen kind of typical light bulb that you're seeing, like that we've been using for centuries. This one is rated to 150 watts and still a single phase. But okay, if we're looking at a single, light bulb that you put in a lamp versus an overhead pendant lighting, this is significantly more. So we could get 3+ different lighting apparatuses of this nature that are LEDs versus only one. So when we're thinking about our critical loads, it's important to understand exactly how much power they need to be the most efficient you can with selecting the size of your inverter and the size of your batteries. So if our inverter is a few kilowatts, it's not going to make a very big difference in terms of power needs for 43 versus 150 watts, because even 150 watts is not very much. But the amount of time you want to stay illuminated is going to matter drastically, because just to power this, even let's say for 1 hour, it's going to be 150 watt hours for a single hour. But for this to power for 1 hour, for 1 hour. But this is going to be, a fraction of that in terms of the energy needs of the battery bank. So I want to be conscientious of identifying the wattages and how long they're going to run and being as efficient as possible. So let's keep going and looking at different applications. So this was a Samsung TV. And again, I was just browsing the internet to find different appliances and find their electrical specifications. So because you want to be as precise as possible in understanding your different loads, I find it easier to go to like data sheets for these products on their manufacturer's website rather than a distributor. So for example, if I'm looking at this Samsung TV, but I want to buy it at Best Buy, I would look at the data sheet on Samsung to make sure that it's a manufacturer, has that level of detail. Because we want to make sure that we understand what the power consumption is, rather than some websites will just provide what overcurrent protection do you need. So it has, let's say, up to 15 amps, but we don't know what it's actually drawing. What we want to understand is what are these appliances actually drawing. So I liked this Samsung data sheet because it included a typical consumption and a maximum consumption. So if we're really going into like TV binge mode, we can assume, or we can rate this item to 48 watts versus if we're just in regular mode, it's only 28. So this is a decent distinction between what you typically would see versus what you would see on a maximum level. So I like to be conservative in my estimates. So I would probably rate this television to 48 watts just so that I know. Again, we're identifying that it's 120 volts and making sure that you know that each of these appliances are 120 versus 240 volts is important, so that when you design your critical load panel, you know to use a single or a double pole breaker. our garage door opener. So in this case, we had it written in amps and watts. Again, it's going to just be a relationship between volts times amps gives you watts. So this is a 5 amp unit at 120 volts. That's going to be 600 watts. So 600 watts, you know, that's a decent amount of power you need to open your garage door. But then when we think about it in terms of the battery needs, how long is your garage door running to open? Maybe 10 seconds, 15 seconds. So the duration is short, but the power needs are relatively high, at least comparatively with our light bulbs and our television. It's an order of magnitude. So all these things go into consideration when you're sizing your inverter and sizing your battery bank. Okay, let's look at some bigger loads. So in our kitchen, you know, during a critical period, you may still want to include, I certainly would want to include my fridge, but other appliances are not, you can still consider larger loads when sizing a battery bank. You just have to understand that they may take more of the inverter draw, and they're going to need more watt hours for the duration that you're going to be running them. So this is another example of a Samsung refrigerator. So this is running at 5 amps, not very much. So I typically will look at refrigerators as 2 kilowatt hours a day, roughly. And they turn on sporadically. You know, it's not actually running. The compressor of your refrigerator isn't running 24 hours. It's normally intermittent. It'll switch on and it'll switch off. But when it does switch on, it's going to be pulling 5 amps. Good to know. And with the 115 volts, so different appliances are rated at different voltage levels. The 115 is suitable on a 120 volt circuit. So that's not something that should be concerning. This is a dishwasher, 12 amps for the draw. So again, this is more than any appliance we've looked at so far. Again, often because dishwasher has the heating element associated with the washer. I mean, the temperature of the water and the dry cycle. So 12 amps, pretty significant. But you would set that maybe to say, if I'm in a critical need, I'm only going to run this once. So let's say you give it a 2-hour amount of time. So you say, I know my 12 amps or my 1400 watts is going to run for 2 hours, and that will help dictate the watt hours needed for your battery bank. So this is just a small Black & Decker, it's an electric oven, a toaster oven. Understanding the power needs of like electric wall ovens was very challenging. So I decided to settle on this toaster oven. And this is rated to 1500 watts. So again, it's designed to make something get hot. So it's going to be a higher wattage level. But the good news is this is a 120 volt load. So if we look at everything we've talked about thus far, if you wanted to say, I'm going to just back up. I want to have my single pendant light, my television, my garage door opener, and my fridge and my dishwasher and my toaster oven. You could have all of these covered on an inverter that runs 120 volts because all of your loads are within the 120 volt range. We're not looking at any split phase loads, so that's something to consider. If I'm looking at all of these 120 volt options, I only need a 120 volt inverter. So something to point out. Again, you probably wouldn't be using a toaster oven for that large amount of the day, but if you're in critical mode and this is the only cooking apparatus you're using, let's say I don't want to use my microwave, I don't want to use my range, I only want to use this toaster oven for heating, be conscientious of what the run times are going to be, because you want to make sure that you can power 1500 watts for a given amount of time. And that's where the battery is going to start draining more and more if you run this continuously for a long period of time.
Madeline?
Yeah.
Do you mind briefly explaining starting amps with the fridge appliance, if
Sure.
possible?
So for the fridge, refrigerators are relatively straightforward appliances. There's mostly just the compressor that turns on. So if we, and you know, it would be nice, maybe another session, I'm going to pull up kind of a evaluation of your load. Like what does it look like for a refrigerator to be powered in a 24-hour period? So let's say it's intermittent and it turns on on the hour for 5 minutes. So that means we're going to be having 24 instances of a 5-minute runtime. We're going to have these 5 amps occurring for 5 minutes and then they're going to stop. So let's just, for example, say once the compressor runs, and if it can keep the fridge for the remaining 55 minutes cool, then it's going to be 5 amps for 5 minutes, and then it's going to be off. So you don't really have to think about it in that way because our battery bank we're sizing over typically a 24-hour period, or you'd be looking at your loads in a 24-hour period rather than saying, okay, in this hour, what am I going to have running at a given moment? Because if you were leaving your fridge, let's say you're cooking a big meal and you leave your fridge door open a lot during the certain time that you're cooking, but then overnight, your fridge door is closed the whole night. So the frequency of it turning on and off really depends on the usage, but again, it's going to be coming in different increments depending on when the compressor turns on, and that's going to be 5 amps when it goes into its like cooling cycle. I hope that makes sense.
Thanks, Madeline.
Sure. Okay, let's talk about some more appliances. So this is our washer. And the washer, because when you think about a clothing washer, what are the different cycles? Okay, you have kind of cold, warm, or hot water. So there is, the water heating element is probably coming from your hot water heater. So that's not necessarily relevant. You're really just thinking about the spin cycles, spin or rinse cycles. So 15 amps is what it's going to take to power your clothing washer. And this, again, is just a typical 120 volt appliance. So not very big. 15 amps is a sizable amount of draw, but single phase. So that's good to know. And then you can kind of calculate, okay, based on my cycle, if I'm only going to do a quick load when I'm during my critical period, you can time that cycle, the quick cycle time, and you say that's going to be the hours associated with my washing machine. But then here we got our dryer. So this is our first look at a 240 volt appliance. So dryers are interesting because they have that 4-prong plug. So you need to have your electrical service upgraded to receive this 4-pronged plug. And because this is a 240 volt 4-prong plug, you know that you're going to be on a 2-pole breaker in your circuit panel. So something to note. So interestingly, this is only drawing 10 amps, but because it's 10 amps at 240 volts, we're looking at a much higher wattage than if we were looking at 15 times 120. So the power needs are greater because our voltage has doubled, even if our amperage has decreased a little bit. So we always want to be considering the total wattage that's going to take to run something when we're looking at sizing our inverter and sizing our battery bank. So if we have taken all of the loads up until this point to back up, now we need to upgrade to a 240 volt supporting inverter because this is our first 240 volt appliance. So we need an inverter that can support that. HVAC. I do want to spend some time on HVAC because it's really illuminating how like air handling is so variable in terms of needs. So this is a window unit. It's a sleek, nice, I Googled window units and this is what came up. So it's a new model. And so 208 versus 230 volts means it can be on like a 208 3-phase or a 230 volt. So you can be running this in different voltage configurations. I'm not going to spend a ton of time on different voltage configurations, but basically the application, this product is going to be running at basically 1600 watts, regardless of if you're in the 208 or the 230 volt setting. But it has the ability to be in both of those settings. So I really want to note that for 1500 watts, I mean, this is barely more than our toaster oven. So that's a really important thing to note, that if we're in dire need and we really need to cook something and we really need to run the air conditioner, we're still only pulling a little more than 3 kilowatts. So it's not bad. So I just want to be cognizant of the wattage values for different appliances. So window unit, 8 amps roughly if we're doing the 230 volt. So really not bad. Moving into a mini split. So a lot of people are not familiar with mini splits. They're kind of a they're like a hybrid air conditioning product. So this mini split, it's roughly 3 feet wide, and they're typically installed like where your wall meets the ceiling. And then this unit, this fan unit, would be outdoors. But it's like an indoor out. It has partially indoor and partially outdoor features, and then you control them on a remote typically, because this is mounted near the ceiling, so you can't manually adjust it the way you would manually adjust a window unit. You have a clicker. So this is a single phase unit pulling 10.4 amps. That is not that much. So normally when we say like we want to be careful about backing up air conditioners, if you have a window unit or if you have a mini split, it's not unreasonable to have one of those running when you're in critical mode. So, I mean, we can't all be fortunate to like build our own homes, but if I ever were to, I would consider having multiple mini splits, because, okay, let's say let's just pretend like you have 2 bedrooms and then a main living room, and you want to have 3 of these units. Even in backup mode, you can run one at a time. You can say, okay, I'm ready to go to bed. I want to cool my bedroom. I'm going to wake up, turn that unit off, go into the room you're going to use, and turn the next air conditioner on. So it's more of a space conditioning. You know, you have to be more conscientious by running it in different locations, but it's very manageable on a battery bank if you're able to kind of control that a little bit more. So here we go, the big monster. This is a central air conditioning unit. So to run full time, typically it's 15 amps. However, with the locked rotor amps for startup, to get these units going, you have a surge value of 63 amps. So what does that mean? We can still set our overcurrent protection on a 20 amp breaker because it's running most of the time at 15.3 amps. However, during startup, for this short period of time, we're not necessarily going to trip the breaker because we're just kind of boosting our unit to get going, but we need an inverter that can support that. We need an inverter to be able to provide the power for a split second. Let's just say a half a second to get this going. We still need to pull 63 amps in that instance. So that's not even inclusive of anything else that you're backing up. Like if I'm running my fridge and a light at the same time that my air conditioner wants to kick in, that means I'm going to need 70 plus amps available for my inverter. That's a lot. So I want to just add the fact that having enough power to start up a central air conditioning unit is tricky. Is it impossible? No. You're going to need multiple inverters stacked to provide power for this single appliance. But when we're looking at backing up critical loads, I want to be modest in my assumptions and ideally would even get a window unit and back up the window unit. I mean, this might be a little crazy, but if you have central air, just get a window unit and back that up for when you're really in dire need. If we're desperate, put it in your bedroom and say, I'm never leaving my bedroom when I'm in critical mode because I can support it. So want to consider the heavy draw associated with central air conditioning units because it's really a lot. And it's just amazing to me to think that, you know, I live in Austin, Texas. So Central Texas, most people have central air, but we're just not even thinking about how much power that's really using because we're grid tied. And thankfully, knock on wood, our grid doesn't go down often. But if I ever were to want to support my house, it would be very difficult to include that. And it's so hot during the summer that you really do need to, even in backup, in an emergency setting, to have some sort of cooling mechanism. So, you know, for any home builders out there, I'm a fan of the mini split. Okay. Let's look at some examples. So this is a pre-wired Outback unit. This is the Radian inverter. They come in a 4 kilowatt 240 volt output and an 8 kilowatt 240 volt output. This is the load center that goes with it. So this is where all the AC and DC wiring happens. This is a charge controller. So this means this is likely a DC coupled system because we have a charge controller, and this is where the solar PV is going to be plugged into. We have two of these charge controllers. And these are FM 100s, I believe. And then this is our mate. This is where we do all the programming. This is how you kind of control the settings of your system. We have 4 SimpliPhi batteries. And then I want to note that we have 2 load panels. So this, I'm just making this assumption based on this photograph, but this is going to be our critical load panel. So if this is our main load panel and this is 200 amps, this is going to have our big appliances that we don't necessarily need, or this is going to have every appliance that we don't necessarily need during backup. So I don't know, maybe like a guest room television, guest room lighting, backyard lighting, like things that you still want to have power to when your house is running at normal, but that you're not going to need a battery backup for. This is where you're going to be putting all your critical loads. So everything that you need when a battery strikes is going to go here. And this is where the inverter, the inverter output is going to run into here, and the battery output is going to run into here so that you can get PV power and the battery feeding your critical loads. Okay. Here's another example, very similar with Schneider. So this is a SimpliPhi Access, and this is the inverter. So this is the 6848, I want to talk about what this naming means. This is really indicative of what this inverter can do. So 68 is referring to the kilowatts of the inverter. So it's 6.8. The 48 is referring to the DC voltage sizing. So it's a 6.8 kilowatt with a 48 volt DC like battery configuration. So these, I'll keep scrolling. Oh, good. Batteries coming next. These are the batteries, and these are 48 volt style batteries. So SimpliPhi sells 12, 24, 48, and higher voltage batteries, but we want to make sure that these batteries are the 48 volt model to pair with the 48 volt output inverter. So again, we have our inverter and our batteries, and those are going to be on a critical load panel. I'm not exactly sure if this is a critical load panel based on this image, but we're going to talk about what the critical load panel does in the next slide. So if we have a 20 amp breaker, typically your load capacity would be between 0 and 60% of the maximum of that breaker. So ideally you want anything up to 12 amps to land on that breaker, but no more than 16 amps. So 80% is our maximum amount on a breaker. In this case, since we're looking at a 20 amp breaker, we don't want more than 16 amps aggregated on that. So since we have 3 batteries at 3.5 kilowatt hours each, our total battery bank size is 10.5 kilowatt hours. So in the event of an emergency, in this case, we have up to 6.8 kilowatts of instantaneous power, and we have 10.5 kilowatt hours for the battery bank with the duration of the needs of this system. Okay, here is a deep dive into the critical load panel. So this is labeled really nicely. If we look, so on this panel, you can see kind of imprinted or stamped in this load panel, we have breaker slots. So 1, 3, 5, up to 13 on the left, and then 2, 4, 6, up to 14 on the right. So we have a 40 amp dual pole breaker on slots 1 and 3. So this is, we have nothing assigned to this. This is just a 40 amp, 240 volt breaker, nothing on it. So let's look at what's on, let's look at what's on these things. So just by looking at this load panel, we have, on most of these cases, up to 20 amps per breaker slot. But because I know that we have a 6.8 kilowatt inverter, we're not going to be running 20 amps in 10 different positions. We're going to be running fewer than 20 amps in 10 different instances or what have you. So I made these assumptions based on these labels so that I can roughly assume that based on these labels, this is a hypothetical system that would work. So lighting at an amp means we're getting 120 watts worth of lights for our first 20 pole breaker. Our fridge, 600 watts if it's a 5 amp fridge, which is similar to our Samsung example. So if it's running 5 hours a day, an estimate, okay, that's 3 kilowatt hours. That may be a little high, but again, this is me speculating. Driveway gate, 30 watts for 30 minutes, fine. Kitchen lighting, again, we're just using 120 watts loosely for lighting. Wi-Fi router, 12 watts. That's gonna be running all the time. So maybe we only need the lights for 4 hours a day. Mini split, here we go. We got our air conditioner. It's a mini split, which is the kind that I like. Okay, this happens to be a 240 volt mini split. That's fine. 10.4 amps. So this is a 2,500 watt appliance. But if it's really hot, we're only running it for 2 hours a day. We're gonna have roughly 5 kilowatt hours. So something I wanna point out. If we have a 10.5 kilowatt hour bank, nearly half of our bank is dedicated to 2 hours of air conditioning. That's significant. So is it possible? Yes. Is it going to take a lot of power? Yes. We can have it all. Night table, 60 watts. Not necessarily sure what we would be powering. Maybe a radio. Pool pump. We get our second 240 volt load. So again, ideally, we are not running, I mean, we can, because the sum of all these loads is still only 6,798 watts at a given time. We could feasibly power all of these appliances at the same exact time. So if our pool pump is pumping at the same time our mini split is running, that's okay. We're just at, 5-ish kilowatts powered. Washer, 7 amps, 840 watts. Decent estimate. So again, for every single appliance running at the exact same time, we're just under 6.8 kilowatts. And then based on these run times that I've assumed for one 24-hour period, we're at 9.3. So if our total battery bank is 10.5 kilowatt hours, and based on these daily estimates, I'm at 9.3. Okay, I get 1.2 kilowatt hours left. This is going to protect me for 25 hours, let's just say. So we have a very decent amount of appliances able to live a normal life to some extent. We're still getting our mini split and we're still getting our pool pump for some amount of time. Again, this is for one day because we're at 9.3 kilowatt hours and our bank is at 10.5. So if we want 2 days, let's say, we would just have to double our battery bank. So we would go from 9.3 to 19 or so. That's it. All right. I hope that this kind of evaluation of looking at the wattages and then how long they're going to run is a good understanding. I'm going to go back, particularly for how to set this up. setting up your critical load panel is, no pun intended, it's critical. A whole house backup is possible, but I'm so much more in favor of setting up a critical load panel so that you know what loads are going to be running. Like, I'm just giving myself a limit on what am I going to be using, and so I can monitor my usage when the outage occurs. Because you don't want to install a system for a customer and then have them come back and say, my battery died so fast. Well, maybe there were loads that we weren't considering to be running on that battery that actually were. So by setting up this very deliberately, your critical load panel is going to be running exactly what you know and for the amount of time you've estimated.